instantaneous sampling, natural sampling, and flat top sampling. So let us begin our discussion with the very first one, instantaneous sampling. I want to instantaneous sampling. So here what we do is we take a multiplier, let it be a multiplier, which multiplies two input signals. Let my output signal be S of t, and I have one input signal as my M of t, and another input signal is my C of t. Keep remember, C of t here is a what?
Pulse train.
Pulse train.
Kind of pulse.
It is a train of impulses. In instantaneous sampling, we take C of t as a train of impulses. Whereas in natural sampling and flat top sampling, we take train of pulses. Okay? So here we take the train of impulses. And M of t is as usual our baseband signal. M of t is the band limited baseband signal. Okay. So if this is the case, that means I have M of t as the input, which is being multiplied with my impulse train C of t, and my S of t equal to simply the product of M of t and C of t. Now, if I have an impulse can be mathematically represented as, say, delta of t, right? Now, instead of a single impulse, I have a train of impulses. So this train of impulses can be mathematically represented as, say, it is the summation of impulses, let n equal to 1 to infinity, delta of t minus n ts. So at every sample time interval, I have an impulse. Okay. So assume AC is the coefficient or the height of the impulse. So therefore, C of t can be represented as AC into sigma n running from 1 to infinity, delta of t minus nts. N is the integer, t is the sampling time. So therefore, if you look into the waveform, how the product will look like, let us consider the waveform. Something like this. So here I have a signal something, M of t is like this, let us suppose, for the timing. Okay. Then my impulse train, I have pulses. At regular intervals of time. So the time between these two is Ts. This is my C of t. Keep remember the width of the pulse, width of the impulse is delta t or simply dt, whatever. Thus delta t is very, very minimum, very, very minimum. Now, because I have my m of t something like this. So at this interval of time, I got my sample. If I multiply these two, so after multiplying these two, m of t and c of t, whenever there is c of t, keep remember, whenever there is c of t, m of t can be multiplied. During the rest of the time period, my c of t value is 0 if you observe carefully. So therefore, if you multiply these two, I'll get the product term s of t, something like this. This is my s of t. Instantaneous sampled pulse amplitude modulated signal is S of t. And the other name for this instantaneous sampling is ideal sampling. Because it is very hard to generate the impulse. Moreover, it is very difficult to generate the train of impulses. The pulse width is infinitesimally small. So therefore, we call it as ideal sampling. So this is the multiplier. One input to the multiplier. You can hear me, right?
Yes, sir.
Yes, sir.
Can you hear me?
Yes,
Yes,
sir.
sir.
Okay. I think there is some break in the network. So the generation is done by using a simple multiplier. One input to the multiplier is m of t, and the another input to the multiplier is the train of impulses. And that impulse train mathematically we represented like this. Therefore, m of t or my s of t can be written as s of t can be written as my output s of t equal to m of t into AC sigma n running from 1 to infinity. I am simply multiplying these two, m of t into c of t, where c of t is already defined as AC sigma n running from 1 to infinity delta of t minus nts. So delta of t minus nts. So this is my time domain expression for the output of ideally sampled pulse amplitude modulated signal. So let us move to the second type of PAM. Second type of PAM is what we call it as natural sampled PAM. So here, instead of using the only difference, instead of using what we call impulse, so we use practically a train of pulses. And a circuit to generate a simple circuit, I can say, to generate is this one. So I use the input to this circuit as M of t. And here I have a switch, and that switch can be controlled by using C of t, where C of t is a train of pulses. C of t is a pulse train. So this is my output S of t. We'll see the waveform first, then we'll go for the mathematics later. Okay. I'll draw the waveform here. For our convenience, I have taken M of t, the same M of t, whatever considered for instantaneous sampling, the same M of t is taken. So I have a pulse train here. Train of pulses is my C of t in the case of naturally sampled pulse amplitude modulated signal. So this is my C of t. So from the above circuit, the switch is closed. The switch is closed during this pulse duration, or when the C of t value is at logic 1 or at 5 volts, the switch is closed. When C of t is 0, switch is open. If C of t is 0, switch is open, then my S of t will become 0. That means here if I write the condition that I'm saying if C of t equal to some amplitude A, 5 volts or 1 volt or 2 volts, the switch is closed. Then my S of t will become, once the switch is closed, S of t will become my M of t, right? Or A into M of t, whatever. A into M of t, more precisely. If C of t equal to 0, what is S of t?
0.
0. Right? So if C of t is 0, S of t will become 0. So apply the same condition. You apply the same condition to generate our PAM signal. So as a result, I can have so this is my first pulse. This is my second pulse. Third pulse. So this is the pulse amplitude modulated signal using natural sampling. So therefore, even here also I can write my S of t as if I convert this switch into mathematics, so I can simply write S of t equal to M of t into C of t. Now you try to get what is the difference between an ideally sampled PAM or a uh, uh, instantaneous sampled PAM and natural sampled PAM. What is the difference? This one and this one. Any difference? An ideal sampled PAM and a natural sampled PAM. I hope my question is clear to you all. What you can identify that there is some difference in uh, natural sampled PAM and ideal sampled PAM.
Here we have considered train of impulses. Here we have considered train of pulses.
Okay.
Even the delta t value is different.
Mhm. So because the carrier here used is different, you are close to the answer, but the actual what I am expecting is uh, see here in ideal sampled PAM, I have a fixed value. If I take the sample value, say let it be 4.3 volts, let it be 3.7 volts, something like that. These are all the unique values or the unique sampled values, only one value. Okay. But whereas here, if you observe the carefully, during the pulse interval, the amplitude of pulse amplitude modulated signal follows M of t. If M of t is changing, decreasing my PAM during the pulse interval, the modulated signal also decreasing. If it is increasing, modulated signal also increasing during the pulse interval. Or what I mean to say here is within the pulse interval, the amplitude is not constant. Point number one. Within the pulse interval or during the pulse interval, S of t amplitude is varying and is proportional to M of t. So you take any pulse, that means the top of the pulse or the height of the pulse is not constant. That means during the pulse interval, whatever the signal that is being transmitted, the power transmitted is also varies. Power transmitted changes within the pulse interval, during the pulse interval. Because the top of the pulse is not constant. Anyway, we'll get back to that point little later, because that will be the input for the third type of PAM, what we call it as flat top PAM, flat top sampled PAM. We'll get back to that. So is that clear till now? We have seen instantaneous sampling, we have seen natural sampling, PAM. Is that clear till now?
Yes, sir.
So, want to explain the difference between ideal sample PM and natural sample PM again, sir?
Okay. In ideal sampling, we are using the train of impulses. And the pulse width here is delta t. This delta t is infinitesimally small, the width of the pulse. Of course, when we multiply C of t with M of t, we got this signal, ideally sampled pulse amplitude modulated signal. So whenever there is a sample, I have a specific value or one particular value of that sample in this entire M of t. Only one value. Let it be, say, 4.27 volts. And this value is, say, some 2.13 volts, something like that. So you take any sample value, you can have a unique value in ideal sampling. Because the pulse width is infinitesimally small, I can take only one value after multiplication. Whereas C of t is changed here in naturally sampled PAM, I have a fixed pulse width of tau, let us suppose. So during the tau duration, during the time interval tau duration, when I multiply C of t with M of t, I got this pulse amplitude modulated signal, something like this. Now this top, because it is following M of t, because you are multiplying M of t with C of t, so therefore this is not a single value. From here to here, it will follow M of t, and the top of the pulse is not just like here. This top is flat, this top is not flat. Now, within this interval of time, tau, whatever the transmitted signal, because my amplitude is varying, power is proportional to amplitude of the signal. Square of the amplitude of the signal. So because my amplitude is varying, my power also varying. So during that interval of time, because my top of the pulse is not constant, my PT is going to change during that interval of time. This is what the difference between the ideal and natural. Because here I have only one value, during that interval, only that fixed value of power will be transmitted.